Hey guys, welcome back to day 42, and today we're going to just do examples of calculating enthalpy. So we'll start with our notes. How much heat? There's a question right off the bat. How much heat is liberated in the combustion of 206 grams of hydrogen? And you've got the H of combustion is negative 286 kilojoules per mole. So H2 gas plus half O2 gas gives us H2O liquid. Plus 286 kilojoules. So we'll start with our 206 grams of H2. And it's 2.02 grams H2 is 1 mole. H2. And 1 mole of H2 happens to be negative 286 kilojoules. That will give us 29200 kilojoules. 29,200 kilojoules. And it's negative, and that just means it's heat released. The next one, top 5. So of the top 5, this would be, I believe, the 4th one, and it's not 1, it's part 2. Propane, and we have the balanced equation for propane right here, is used in many instances to produce heat. It gives you the standard enthalpy of the reaction. How many grams of oxygen will be needed to produce 500 kilojoules of heat? So we have 500 kilojoules. And what has to go on the bottom? It has to be kilojoules. Well, we have this number, negative 2044 kilojoules, and that relates to 5 moles of O2. And then we're going from moles of O2, 1 mole of O2 to grams of O2. And it happens to be, I need to write this a little bit better here, 32.00 grams of O2. If we do that, I get negative 39.1 grams of O2. Can we have negative grams? Of course, the answer is no. All this means is that we are exothermic. Got to have positive grams. You can't have a negative mass. It doesn't work that way. Number 2, still with this reaction. A swimming pool is 20 meters long, 2 meters deep, and 5 meters wide. Let's draw a picture. So it's 20 meters long, 5 meters wide, and 2 meters deep. Okay. Fill with water. The temperature of water is 22 degrees Celsius. But the owner of the pool would like the temperature to be 32, so we want to heat it to 32 degrees Celsius. That's really warm. Here's our question. How many grams of propane would have to be consumed if all the heat from the combustion was to be absorbed by the water? Wow. Okay. Well, first, how much water do we have? Well, we can figure out that we have 20 meters. The volume of my pool is 20 meters by 5 meters by 2 meters. So that's, what, 200 meters cubed? There's the volume of the pool. We are changing the pool 10 degrees Celsius. And I have a formula for that. So to change the temperature of the pool, this delta T, that would be a Q equals MC delta T. C is a constant. I can look that up. Delta T I have in blue there. I need the mass of the water. I have the volume of the water. So we're going to have to find the mass H2O. If I have 200 meters cubed of H2O, I know that for every 1 meter cubed of H2O, there are 1,000 liters of H2O. And for every 1 liter of H2O, there is 1,000 milliliters of H2O. And we know the density of water for every 1 milliliter of H2O liquid, it is 1.0 grams of H2O. So that gives me 2 times 10 to the 8th grams of water. So now I have Q equals MC delta T. I can heat the water. So the amount of heat required is equal to 2 times 10 to the 8th grams of water times the 4.184 joules per gram degrees Celsius. And delta T was 10 degrees Celsius. 32 degrees Celsius minus, 22, which is just 10 degrees Celsius. So that means my heat that I need is 8.4, 8.368, 8.4 times 10 to the 9th joules, or 8.4 times 10 to the 6th kilojoules. Now we can figure out how much propane. So we're going to start with this 8.4 times 10 to the 6th kilojoules. And we know, again, it's negative, but that negative means it's exothermic. 2,044 kilojoules is required with 1 mole of C3H8. And then we know that 1 mole of C3H8 happens to weigh 44.11 grams of C3H8. That gives me basically 1.81 times 10 to the 5th grams. It's positive, right? This just means, again, exothermic. Or 181 kilograms of C3H8. That's a lot of kilograms of C3H8. It's a good size pool. That's the pool problem. What do we do? Well, I figured out the volume of the water. I figured out how much energy I needed to put into the water. And then we figured out how much propane required to burn to get that temperature of the water. Number 3. Consider the following reaction. It gives you C2H4 plus F2 going to C2H4F2. It gives you delta H. We are to estimate the carbon-fluorine bond energy given. It gives you the CC bond energy is 347 kilojoules per mole. C double bond C is 614. And FF is 154. So I'm giving bond energies here. Which leads me to be delta H equals the energy of bonds broken minus the energy of bonds formed. Well, what's formed here? So C2H2, Lewis structures. I have carbon has 4 valence electrons. So that's 4, 4, and then hydrogen has 1 each. So that's 12 electrons. H, C, H, C, H, H. 2, 4, 6, 8, 10, 12. Perfect. F2. 2, 4, 6, 8, 10, 12, 14. Each fluorine has 7 electrons, so that's 14. That's good. And what we're doing here, C2H4F2, it doesn't necessarily matter how you draw it, but I'm going to draw it this way, where we have F, H, well, and we have the 12 and the 14 electrons, so that's a total of 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. There we go. What bonds are broken? Bonds broken. Well, it looks like the C double bond C is broken and the FF is broken. The CHs look like they stay. Bonds formed would be CF, CC, and CF. All right, the CHs are not there, and they're not even given to us. Okay. So delta H, can't use that line. Delta H of my reaction would equal, we're going to say bonds broken minus bonds formed. Delta H is bonds broken minus bonds formed. The broken bonds would be in the reactants, and that's a C double bond C and F single bond F. The bonds formed would be C, C, and C, CF. And there are 2 CFs. All we're going to do is plug in our numbers now. Delta H of the reaction is negative 549 kilojoules per mole equals the C double bond C happens to be 614 kilojoules per mole, and the FF happens to be 154 kilojoules per mole. The C single bond C is 347 kilojoules per mole. And we have 2 times CF, which we don't know what CF is. We have 2 of them. Okay, so now we got to, let's just get out the parentheses here. I got negative 549 kilojoules per mole equals, this happens to be 768 kilojoules per mole minus 347 kilojoules per mole minus 2 times CF. So I had to distribute that negative 1 right here. Well, bring everything over to the left-hand side. I will get negative, 970 kilojoules per mole equals negative 2 times CF. So that means CF, the bond energy is around 485 kilojoules per mole. And that's all we did there. For the balanced equation for the reaction of methane with oxygen gas forming carbon dioxide and water. Okay, so methane, CH4 plus O2 going to CO2 plus H2O. So 4, put a 2, and I think a 2. I think that's it. I think it's balanced. Bonds broken minus bonds formed. So methane, hopefully you drew that one enough. O2, CO2, and H2O. Hopefully we've done this enough. So 2, 4, 6, 8, 2, 4, 10, 12, 2, 4, 6, 8, 12, 14, 16, 6, 8. Okay. We got to list the bonds broken, bonds formed. So the bonds broken would be CH, O2s, formed COs, and OHs. Then, based upon the energies listed below, not all may be needed, calculate the energy released when 78.2 grams of methane is burned. So delta H of the reaction is equal to energy of bonds broken minus bonds formed. Delta H, bonds broken. I have CH, and I have OO. And just so we know, I was in class show you this is, and this is here. Those are double bonds. They're just not in mine. I need to put equal signs in there. Bonds broken. And now we have 4 there and 2 there, because there's a 2 in front of O2. Formed, I have C double bond O and O to H. And we have 2 COs, and I have 1, 2, 4 OHs. And the reason we have 4 H's, there's 2 moles of water and there's 2 OH bonds per water. Now we're just plugging numbers in. Delta H of the reaction will be equal to 4 times CH, 413. And 2 times O is 732. Minus 2 times CO happens to be, oh wait, I messed up. CO is 732. And OO is not 732, is it? OO happens to be 498. And 4 times OH is 463. Delta H for the reaction, I get negative 668 kilojoules per mole. So now we have to use 78.2 grams of methane, which is right there. So I have 78.2 grams of methane. We know that methane is 12 and 4. 16.05 grams of CH4 is 1 mole of CH4. And 1 mole of CH4 produces negative 668 kilojoules. I get 3250 kilojoules produced. So it's bonds broken minus bonds formed, and then we had an amount of methane. Using the delta H we calculated, how much heat did you produce? next one. Tin. Given tin and chlorine going to tin 2 chloride, and then tin 2 chloride plus chlorine going to tin 4 chloride. Calculate delta H. Well, this problem at one point years ago was an actual test question, and it should have been extremely easy. Reactants: tin and chlorine. 1 2 chlorines, 1 tin. Products: tin 4 chloride. Intermediates: that one and that one. So if you add them up, the pink goes away. All right, so all you'd actually have to do is add these two up. So that's 325 and 186. They're both negative, so it's negative 511. That was a test question. It was supposed to be a nice, easy, like relief. They're lined up. Let's go, shorter than the 3 minutes per question target. And almost everybody got it wrong. Because they overthought it. They were flipping things and doubling things, and I don't know why they were doing that, but they were doing it. So don't panic on a test. Just do the process. Acetylene reacts with oxygen gas and to form carbon dioxide and water. Write the balance equation. Okay. So C2H2 plus O2 going to CO2 and H2O. We have gas, call it a liquid or a gas, either way. Balancing, 2, put a 2 there, that's good, that'll be odd, so we're probably going to do a 2. We'll have to do a 4, we'll have to do a 2, and we'll have to do that to what? 5? Yes, 5. So now we're balanced. We're given the standard enthalpies of formation. So given the following enthalpies of formation, how much energy is released? There's a question. And we're starting with 3 moles of acetylene. So we have 3.0 moles. How much heat? Well, delta H of the reaction, sum delta HF products minus the sum delta HF reactants. Delta H standard products. My products would be CO2 and H2O. Reactants, C2H2 and O2. There are 4 CO2s, 2 waters, 2 acetylenes, and 5 oxygens. Delta H standard of the reaction would equal 4 times CO2, which is negative 394 kilojoules per mole, and 2 times water, which is negative 286 kilojoules per mole. Minus 2 times acetylene is 227 positive plus 5 times water. And what is water? 5 times oxygen, excuse me. What is oxygen? Oxygen, of course, is 0 because it's an element in a standard state. That's why it's not listed. So we do this math. Delta H standard of our reaction should be negative 2602 kilojoules per mole. And now we have 3 moles of acetylene. So 3.00 moles of C2H2 times, we know that it's 2 moles of C2H2 to negative 2602 kilojoules. So that gives me 3903, or negative 3900 kilojoules. Sig figs, I have 3, so this would be better be 3.90 times 10 to the third kilojoules. Negative means it's released. Last one, just like the one before. We're going to balance the equation for the reaction of ethanol with phosphorus trichloride, forming ethyl chloride and phosphorus acid. Then calculate the heat of the reaction. So we got to write a balanced equation first, calculate the heat of the reaction, and then calculate the standard enthalpy change when 39.2 grams of ethanol is consumed. CH3CH2OH plus PCl3 going to C2H5Cl plus H3PO3. All right, balancing. I would need a 3 for chlorine here, and a 3 here, and I think that's balanced. I have 6 carbons, 3, 5, 15, 3, 1, 1, 3, yep, that's balanced. Delta H is equal to the sum of the standard enthalpies of formation of products minus the sum, the standard enthalpy of formation of the reactants. Products, delta H, standard of the reaction. Products would be C2H5Cl and H3PO3 with 3 C2H5Cl. Minus reactants, I have CH3CH2OH and PCl3. And there are 3 ethanols. Plugging in numbers. Delta H, standard of the reaction, would be 3 times negative 105, it looks like. Yes, negative 105 kilojoules per mole, plus H3PO3 would be negative 972 kilojoules per mole. Minus 3 times that one's negative 277 kilojoules per mole, and plus a PCl3 would be negative 287. Delta H then of the reaction seems to be negative 169 kilojoules per mole. Then 39.2 grams of ethanol. So we have 39.2 grams of CH3CH2OH. 1 mole of CH3CH2OH. 46.08 grams of CH3 CH2OH. Mole ratio, 3 to 1. 3 moles of CH3CH2OH, negative 169 kilojoules. I get 47.9 kilojoules, if my math's correct. That concludes day 42, calculating enthalpy. That's all the enthalpy problems we will do. Again, if you have questions, feel free to contact me. Otherwise, take care, guys. Have a great day, and we'll see you next time.